All right, high school physics students, let's jump right into this explainer and crack the cosmic mystery of orbital mechanics. If you've ever looked up at our moon and just kind of assumed it's permanently locked in place, doing exactly what it's done since the dawn of time, well, you are in for quite a shock today. Our solar system is incredibly dynamic. It's this constantly shifting, moving, and evolving gravitational dance. And today we're going to look at the exact physics that determine whether a moon is destined to survive, escape, or be completely obliterated by its host planet. Here is our roadmap for today. First, a tale of two moons. Second, the synchronous orbit limit. Third, escapers versus the fallers. And finally, the future rings of Mars. So, part one, a tale of two moons, the Martian paradox. Let's kick off our case study by taking a quick trip over to Mars, a planet with two moons experiencing wildly different destinies. Mars is orbited by Phobos and Deimos. Now, they might look like two standard rocky companions, but they are actually starring in a high-stakes, slow-motion drama that completely baffled observers until the underlying physics were properly understood. It brings up a really fundamental question. Are moons falling toward their planets, or are they escaping into space? To figure that out, we have to look at a literal tug-of-war happening right over our heads. You see, the relationship between a planet and its moon is this super delicate balance of gravity and momentum. And when we look closely at Mars, we realize that orbiting doesn't actually mean staying still. It means you are either falling inward or you are running away. It's a brilliant contradiction, honestly. Phobos is basically locked in a spiral of death, while its sibling, Deimos, is just running away. Phobos is actively falling toward Mars, getting about 2 meters closer every single century. But Deimos, orbiting the exact same planet, is doing the exact opposite. Just like our own moon here on Earth, Deimos is slowly drifting away from Mars and will eventually escape its gravitational hold entirely. So how can two moons captured by the very same planet have completely opposite fates? Is it because of how much they weigh, or maybe how they originally entered orbit? Actually, no. That brings us to part two, the synchronous orbit limit, the invisible boundary. Let's transition from the what to the why and uncover the core governing rule of physics behind this whole mystery.
So, here is the crucial point. A moon's survival isn't about its weight or its origin, it's all about its position relative to this invisible line. The synchronous orbit limit is that exact critical distance where a moon takes the exact same amount of time to orbit the planet as the planet takes to spin once on its axis. This is the tipping point. If you're a moon, where you sit relative to this invisible boundary dictates your entire future.
Think of it kind of like a giant cosmic whirlpool. Gravitational drag steals energy from the moons that are too close, and it pushes away the ones hanging out on the outside. Let's break down those mechanics. Phobos is positioned really close to Mars, well inside that synchronous limit. Because of this, it actually orbits Mars faster than Mars rotates on its own axis. Or, in some cases, a moon might have a retrograde orbit, meaning it's moving in the complete opposite direction of the planet's spin. Both scenarios create incredible tidal friction. It's a gravitational brake that literally robs the moon of its energy, pulling it slowly downward. Deimos, on the other hand, is farther away, comfortably outside the limit. It orbits slower than Mars spins. Because of that, the gravitational tug of Mars actually pushes Deimos outward, accelerating it into a higher, safer orbit. To really grasp the intense friction of a moon trapped inside that whirlpool, get this. Phobos is moving so incredibly fast, it orbits Mars 3 times in a single day. Just imagine standing on the surface of Mars and watching your moon rise and set 3 separate times before you even go to sleep. That extreme speed inside the synchronous limit is exactly what generates the massive gravitational brake that is currently dragging Phobos to its doom. All right, part 3, escapers versus the fallers, a solar system matrix. Because, Mars isn't just an isolated incident. Let's apply this new physics concept to the rest of the solar system to prove it's a universal law. What's really fascinating here is how cleanly the relationship between speed and destiny maps out across entirely different planets. When the orbital speed is slower than the planet's rotation, like Earth's moon or Mars's Deimos, the ultimate fate is always escaping. But when the orbital speed is faster than the planet's rotation, or if the moon is retrograde, meaning it orbits backwards compared to the planet's spin, like Phobos or Neptune's Triton, the ultimate fate is a catastrophic collision. The physics hold true no matter where we look in the dark. Let's look at the escapers first. Because they orbit slower than their planet spins, the planet's gravitational pull literally pushes them into a higher orbit. Most of the large moons in our solar system actually fall right into this category. Our very own moon is retreating from Earth at a rate of about 3.8 centimeters per year. Over at Saturn, the giant moon Titan is escaping the ringed planet way faster than scientists originally thought. And of course, our buddy Deimos is riding this exact same outward current away from Mars. And then, on the flip side, we have the fallers. These guys orbit faster than the planet rotates, or they orbit totally backwards, which means gravitational tidal friction is just constantly robbing them of their energy. Phobos is our most famous example, condemned simply because it formed or was captured just a little too close to Mars. But look at Triton around Neptune. It is the only large moon in our solar system with a retrograde orbit. Because it's spinning backwards relative to Neptune, it's constantly losing energy and will inevitably crash into the ice giant in a few billion years. Even mighty Jupiter has fallers. Its small inner moons, Metis and Adrastea, are below that critical limit and are slowly creeping toward the gas giant right now. Which leads us to our final chapter, the future rings of Mars, a cosmic demise. We've established that Phobos is falling, but what actually happens when a moon finally loses its battle with gravity? I promise you, it's not just a simple thud on the surface. Well, if we map out this chronicle of a death foretold, we see exactly how it ends. Right now, Phobos is doing its inward spiral. But fast forward 30 to 50 million years. As it gets closer and closer, the gravitational forces from Mars are going to become so intensely uneven on the moon's surface that Phobos likely won't even make it to the ground. Mars's gravity will actually tear the moon to pieces before it impacts. All of that shattered rock and dust will spread out, wrapping around the red planet to form a brand new, absolutely stunning planetary ring. Mars is going to end up looking like a miniature version of Saturn. I am going to leave you with that provocative thought to ponder, and I really hope this explainer helped you master the incredible physics of our dynamic solar system. Just imagine standing on the red dirt of Mars 50 million years from now, looking up not at a single solid moon, but at a brilliant ring of debris arcing across the sky. It's a huge reminder that our solar system isn't just a static painting. It's a wildly active, ongoing machine governed by these absolute rules of physics. Thanks for hanging out with me to explore the synchronous orbit limit today. Keep studying hard and keep looking up.